The author was fascinated by computers and games from a young age, intrigued by the underlying rules and ideas. He saw both opportunities and limitations in the artificial behaviors and intelligence of early video game characters. He wondered if the minds of humans and animals could also be explained as rule-based computations. This led him to study philosophy, psychology, and eventually artificial intelligence. The author came to realize that video games could be useful tools for studying and developing AI, as well as vice versa, using AI to improve games. His early work focused on simulating natural evolution to develop controllers for robots. However, he found games to be a cheaper and faster alternative to physical robots for experimentation. Through working with games and AI, the author came to see opportunities for using modern AI methods to improve game design and level generation, while also considering human thinking and intelligence. In summary, the prologue traces how the author's lifelong interest in intelligence in games led him to explore the intersections of AI for games and games for AI. Here is a summary of the key points in the chapter. 1. The first working digital computers were developed in the late 1940s and were immediately used to play games. Alan Turing wrote a program for playing chess by hand in 1948 when computers were not powerful enough yet. 2. Chess was chosen because it has simple rules, is widely played, and is seen as a serious, intellectual game with depth and strategy. It was thought to embody the core of intelligence. 3. The very first AI researchers attempted to build programs that could play classic board games like chess, as they thought that mastering these games required intelligence. 4. Eventually, AI programs succeeded in beating human players at games like chess and checkers. However, this did not necessarily mean that the programs were actually intelligent. 5. The chapter questions whether you need to be intelligent to play games well, or conversely, whether playing games well indicates intelligence. Games seem to challenge many cognitive abilities but also teach players how to play them. 6. The chapter sets up the questions that will be explored in further chapters. What is intelligence? What is artificial intelligence? And how can games help us understand and develop AI? That's a high-level summary of the main points in the first chapter. Let me know if you have any other questions. Here is a summary of the MONS 3.0 license. The MONS 3.0 license allows others to keep improving upon your work by keeping it open source. The following are the key points of the license. 1. It is an open source license, meaning it allows others to modify and distribute the work. 2. Modifications and distributions of the original or modified work must also be released under the MONS 3.0 license, thus keeping it open. 3. The license requires credit to be given to the original creator. 4. The license allows both commercial and non-commercial use and distribution of the work. 5. The license offers no warranty and the authors of the original work are not liable for any damages caused by the use of the work. In summary, the MONS 3.0 license is a permissive open-source license that allows others to modify and distribute your work as long as they also release it under the same license, attribute the original creator, and do not hold the original creator liable. The purpose is to enable continual improvements to the work by the wider community. 1. The author asks the reader to choose between playing chess, Super Mario Bros., or Angry Birds to illustrate some common characteristics of playing games. 2. The author argues that when playing games, people plan their moves, think spatially, and try to predict how the game and opponents will respond. These require elements of intelligence. 3. When playing chess, players plan several moves ahead to achieve checkmate or capture opponents' pieces. They also anticipate opponents' counter-moves. 4. In platform games like Super Mario Bros., players plan routes to maximize rewards while minimizing risks. They also estimate jumps and passages to navigate through levels. 5. In Angry Birds, players plan the trajectory and order of throwing birds to maximize destruction using the fewest birds. They also judge whether birds will fit through narrow spaces. 6. While predicting opponents is important in chess, games like Super Mario Bros. And Angry Birds mainly require predicting how the game will respond to accomplish goals. That covers the key takeaways from the provided text regarding whether playing games requires intelligence. Let me know if you would like me to expand or modify the summary in any way. Here is a summary of the key points in the passage. 1. Games require different forms of intelligence and cognitive abilities to play. They exercise skills like reasoning, memory, spatial awareness, decision-making, motor skills, etc. 2. Psychometric theories identify around 11 broad cognitive abilities that are used in games to varying extents depending on the game genre. 3. While playing games does not feel like work, it does improve your cognitive skills as you learn through playing. As you progress in a game, the challenges become harder, but you also become more skilled at handling them. 4. The author argues that learning is the main reason games are fun. Well-designed games offer a smooth difficulty progression that allows you to keep learning as you play. 5. When you can no longer learn or progress in a game, it loses its fun, so games aim to stay accessible while also being deep enough to provide new challenges. In summary, the passage discusses how playing games requires and improves various forms of intelligence and cognitive abilities. Games are fun mainly because they provide an environment where you can learn and build your skills through progressive challenges. Here is a summary of the key points regarding definitions of intelligence in the Turing test. There are many proposed definitions of intelligence, but no consensus. This indicates it is a complex topic still being studied. The Turing test proposes that if a computer's responses are indistinguishable from a human's, it should be considered intelligent. Some argue passing the Turing test is sufficient to demonstrate intelligence, while others disagree for various reasons. Some objections to the Turing test argue text-based communication is limited and does not capture the full range of human intelligence. The Turing test assumes humans are the standard for measuring intelligence, but this can be questioned. Another standard besides humans could be proposed. More broadly, defining intelligence poses challenges because the concept is complex, relative, and based on human judgment. There is no simple, objective definition. Does this cover the main points regarding definitions of intelligence in the Turing test discussed in the passage? Let me know if you would like me to clarify or expand on any part of the summary. Here is a summary of the key points in the given passage. 1. The passage argues that comparing human and computer intelligence is not straightforward. It depends on what specific tasks and problems are used to measure intelligence. 2. Computers excel at performing specific tasks like calculations, memory recall, and pattern recognition. But they lack the ability to perform well in a variety of situations, which is characteristic of real intelligence. 3. The passage draws an analogy with animal behavior. Animals show adaptive behavior suited to their ecological niche. Comparing the intelligence of different animals without specifying the problem or environment makes no sense. 4. The concept of elephants don't play chess is used to illustrate that intelligence is specific to the tasks an organism needs to perform to survive and reproduce. General problem-solving ability is not necessary. 5. Behavior-based robotics, which connects inputs directly to outputs using simple rules, can outperform more advanced robots. This is because general intelligence is not needed, focused competence for a specific task is sufficient. In summary, the key point is that meaningful comparisons of intelligence need to be based on specific tasks and problems that take into account the different cognitive strengths of humans and computers. Generalizations about which is more intelligent are often flawed and miss this point. The summary would be: defining intelligence and artificial intelligence is difficult and prone to flaws and shortcomings. Judging intelligence based on a single test like the Turing test has limitations. A machine passing the Turing test may still lack general intelligence. Defining intelligence as adaptive behavior is helpful but does not allow us to compare different agents' intelligence. Specialized intelligence is not the same as general intelligence. Trying to measure universal intelligence by performance on all possible tasks is impractical and the measure is not computable. A pragmatic definition of artificial intelligence is the quest to make machines that can do things humans can do, but better. This includes narrow AI and does not require general intelligence. There has been successful narrow AI that enabled many technologies we use today, even if general AI remains elusive for now. In summary, defining intelligence and artificial intelligence remains challenging and imperfect. But pragmatic definitions focused on performance rather than conceptual understanding may be most useful for advancing AI research and technology. Does this adequately summarize the key points? Let me know if you need me to clarify or expand on anything. Here is a summary of the key points in the chapter. 1. The so-called AI in most video games is rather simplistic and limited. It controls non-player characters, NPCs, like enemies and allies. 2. The AI is often implemented using a finite state machine architecture. The NPCs have a set of states, and each state dictates how the NPC behaves. 3. An A pathfinding algorithm is commonly used to determine how NPCs navigate from one point to another. 4. The AI controlling NPCs lacks many aspects of a complete mind. They cannot adapt, come up with new plans, or reason beyond the limited set of behaviors assigned to them. 5. While some modern games have more sophisticated AI that allows for planning and coordination, most video game AI is rather rudimentary compared to true intelligence. In summary, the chapter argues that though the term artificial intelligence is often used to describe NPC behaviors in games, in reality the AI controlling NPCs is quite limited and lacks the flexibility, adaptability and complex reasoning of a true intelligent mind. It accomplishes only the narrow tasks it was programmed for. Hope this summary helps. Let me know if you have any other questions. Here is a summary of the key points in the text. Today's NPCs in video games have limited behaviors and abilities coded in by designers. They are not truly intelligent. They follow pre-programmed scripts and algorithms. When the author was a child, he imagined NPCs in video games having much more possibility and intelligence, able to react and interact in novel ways. The author presents a futuristic scenario where video games have actual AI, allowing for open worlds, natural language interaction, adaptive gameplay, and varied sub-games invented on the fly. NPCs behave in believable ways. The game engine would be able to suggest tweaks and fill in details to help the player design their own game, fleshing out game ideas into fully playable experiences. Artificial players would also test and demonstrate parts of the game. In summary, the text contrasts the limits of today's non-player characters and programmed game mechanics with the author's vision of what video games could be like if they utilized more advanced artificial intelligence. The futuristic scenario illustrates some of the possibilities for more intelligent and adaptive gameplay. Here is a summary of the key points in the passage. 1. The idea of an AI that can develop and learn on its own without much human programming is appealing both to AI researchers and businesses. 2. One way to achieve this is through an evolutionary approach, simulating how natural selection shapes organisms over time. 3. The core idea of evolution involves three things: variation, heredity and selection. 4. Variation means there are differences among individuals in the population. This allows for heredity, where offspring resemble but are not identical to their parents. 5. Selection means that some individuals have more offspring than others due to differences in fitness. Fitness is approximated by the number of grandchildren an individual has. 6. The author uses the example of rabbits to illustrate these concepts. There is variation in size, color, aggressiveness, etc. among rabbits. Offspring resemble but are not exact copies of their parents. Larger, more aggressive rabbits are likely to have more offspring. 7. The author argues that simulating this evolutionary process in computers could lead to AI systems that develop and optimize themselves. Here is a summary of the provided text. Rabbits may have evolved longer legs so they can run faster from foxes and sharper eyesight to spot predators from afar. This is due to heredity and evolution through natural selection. The DNA of a rabbit contains the blueprint for its traits. Through sexual reproduction, the DNA of parent rabbits is recombined in offspring. Mutations also occur due to errors during cell division. Rabbits that escape predators are able to reproduce more, passing on genes that help them evade foxes. This selects for traits like longer legs and better eyesight over many generations. Similarly, foxes that catch rabbits reproduce more and pass on advantageous traits, creating an evolutionary arms race. Over time, both species become better adapted to catching/escaping each other. Evolutionary algorithms can be applied to computer programs. Programs are given variations in offspring through mutation and recombination. Programs that perform a task better are assigned higher fitness and selected to produce offspring, while poor performers are discarded. Over generations, programs improve at the task. Neural networks are a good way to represent programs for evolution. Small mutations to neural networks are less likely to break the program. A simple feed-forward neural network is described that contains multiple layers of connected neurons that propagate activations forward. Hope this summary helps. Let me know if you have any other questions. Here is a summary of the key points regarding weight of connections in neural networks. Neural networks consist of neurons connected by weights. The weights determine how much influence one neuron has on another. The activation of a neuron is passed through a nonlinear function before being sent to the next neuron. This improves the capability of the neural network. the weights define what the neural network is capable of doing. A network with random weights will not be good at anything. Weights can be trained using evolutionary algorithms or backpropagation. Evolutionary algorithms make small random changes to the weights. Networks with higher fitness on a task propagate their weights to the next generation. The fitness function determines what the network is rewarded for. A good fitness function is important for the network to learn the desired behavior. Training a network on a single track leads to overfitting. Training on multiple tracks creates a more general driving ability. When competing against other cars, a naive network will cause collisions. A relative fitness function based on race position can encourage avoiding collisions. So in summary, the weights of connections determine the behavior of the neural network, and training algorithms aim to adjust the weights to achieve a desired outcome based on the chosen fitness function. Here is a summary of the key points in the provided text. 1. Games can potentially learn from players as players supply information while playing through their actions and choices. This includes button presses, character decisions, and gameplay choices. 2. The player information provided while playing, such as choices and actions, can be expressed numerically and computationally, making it possible for games to learn from it. 3. The information players supply while playing a game could potentially be used to learn about the player, such as their play style, preferences, and skills. Algorithms could be developed to extract such insights from player interactions. 4. Player actions and choices range from complex strategic decisions made over an entire game to moment-to-moment reflexes like jumping at the right time. All of this provides data that games could analyze. 5. Most current games do not actually learn from players as they play. However, the idea that games could potentially gain insights into players through analyzing their gameplay is interesting and could be realized in the future. In summary, the key takeaway is that many modern games are dumb in the sense that they do not adapt to or learn from individual players. However, in theory, the data generated through player interactions could be used to gain insights into players and even tailor the gameplay experience, though this capability is largely unrealized today. Here is a summary of the provided text regarding computer games learning from players. 1. Modern computer games can collect a large amount of data from players, including their inputs, actions, and play history, i.e.s. 2. With this data and machine learning techniques, games can learn various things about players. For example, they can predict how an average player would act in any given situation using supervised learning and neural networks. This allows them to create AI agents that behave like humans. Identify different player types or archetypes based on how players behave and what they prefer. This helps game developers understand and target their audience. 3. Games can learn about individual player skills, likes/dislikes, and tendencies within the game by analyzing the data collected from that player. 4. The large amount of data collected from many players also allows games to identify broader player archetypes using machine learning clustering algorithms. 5. Being able to learn from players in this way helps games personalize the experience and improve features to better match different player preferences. So in summary, the key points are that computer games can gather a lot of information about how players act within the game, and then use machine learning to gain insights into both individual players and broader player populations. This data-driven knowledge allows games to become smarter and more tailored to their human players. Here is a summary of the key information. Researchers were able to identify 4 main types of players based on their gameplay data: veterans, solvers, runners, and pacifists. They were able to create rules that predicted with 76.7% accuracy which level a player would stop playing based on their early gameplay. This shows that players are actually quite predictable in how they play games. Researchers hypothesized that a player's real-life motives may shine through in how they play games. They studied Minecraft players to test this. They had 100 Minecraft players fill out questionnaires to determine their life motives. They also collected data from the players' Minecraft log files. By correlating the game data and life motive data, they found some correlations. This suggests that a player's real-life motives may be expressed in how they play games. The key takeaways are that analyzing gameplay data can reveal player types and predict future player behavior, shows that players are actually quite predictable, may reveal aspects of a player's real-life personality and motives that influence how they play. This type of data-driven analysis of player behavior could help game developers better understand and cater to different types of players. Here is a summary of the provided passage. The passage argues that creativity can be automated using artificial intelligence techniques, contrary to common beliefs. The author discusses an experiment from 2006 where they used an evolutionary algorithm to generate levels for a racing game. The two main challenges were how to represent the racing tracks so that evolution could optimize them, and how to determine how good a track is via a fitness function without actually having humans evaluate them. They encoded the tracks using B-splines, representing them as lists of numbers. However, determining a track's fitness or enjoyability was much more difficult. They realized that accurately simulating what a human would think of a track is currently impossible. Overall, the passage argues that creativity is not fundamentally different from other human capabilities that we aim to automate using AI. While fully automated game design is still out of reach, AI techniques could help augment human creativity for design tasks. The key points are: creativity can be automated using AI, contrary to common beliefs that it requires human ingenuity. An experiment is described where evolutionary algorithms were used to generate racing game levels. Accurately representing and evaluating the quality of game levels was a main challenge. The author argues that creativity is automatable, though fully automated game design remains difficult. AI could augment, rather than replace, human creativity for game design and other tasks. The summary is: procedurally generated content has been used since the early days of video games to create vast game worlds within limited hardware constraints. Rogue, an influential early role-playing game from 1980, automatically generated a new dungeon layout for every game session using a simple algorithm. This ensured each playthrough felt fresh. The success of Rogue led to the creation of the roguelike genre, where randomized levels are a defining feature. Many other games today also use procedural content generation, including Minecraft and the Civilization series. Elite, another early game from the 1980s, generated a galaxy of thousands of planets and star systems as the player explored them. It achieved this by generating each system's details when the player first visited it, based on a random seed. In summary, procedural content generation has allowed game developers to create large, varied game worlds within strict hardware limitations, and has become a foundational technique for many modern games. Here is a summary of the provided text. The text discusses procedural content generation in games. It starts by describing how early games like Elite and Rogue used algorithms to generate game content like star systems and dungeons instead of storing all content. This reduces storage requirements but can sometimes lead to unbalanced or unfair content. The text then talks about using search-based algorithms to optimize generated content for qualities like balance and difficulty. This allows generation of content for a wider range of games. The authors then wanted to generate content tailored specifically for individual players based on their playing style and preferences. They collected data from players of an Infinite Mario clone and used neural networks to model player experiences like fun, frustration and challenge. They then used this mode, L as a fitness function to search for level parameters that would maximize the desired experience for a player. This allowed them to generate personalized levels. The text then mentions that procedural generation is commonly used for background game elements like vegetation but is more difficult for core game mechanics. It discusses how Cameron Brown's PhD research generated complete recombination games like checkers using an evolutionary algorithm. In summary, the text discusses how search-based algorithms and player modeling can help improve procedural content generation in games, from levels to complete game rules, and even generate personalized content. Here is a summary of the key points in the passage. 1. AI methods have potential in playing games, modeling players, and generating game content as seen in previous chapters. 2. However, these methods are not used more widely in actual games yet for various reasons. One reason is that the game industry is risk-averse due to its business model. 3. The current chapter focuses on the role of game design in enabling AI, and vice versa. AI can enable new design possibilities. 4. Tools that combine AI algorithms and human designers, like Tanagra and Sentient Sketchbook, show the potential for greater use of AI methods in game design. 5. While AI-assisted design tools may become more common, it is still uncertain whether modern AI methods will be applied widely within actual games anytime soon. The key takeaways are that while AI has shown promise in certain areas related to games, there are still barriers to its wider adoption in real games. Game design that accounts for AI's capabilities and limitations, as well as AI that can enable novel designs, may help address this. However, there are still open questions about the timeline for widely integrating modern AI within actual games. Here is a summary of the provided text. The author initially tried to convince game developers to incorporate advanced AI techniques into their games. However, the developers responded that AI was not necessary for their games to function properly. Many games were designed around the limitations of AI at the time they were created. Video game genres were defined in the 1980s and 1990s when AI was much less advanced. Games were designed to accommodate the simplistic AI capabilities available at the time. As design conventions crystallized around the lack of AI, developers continued following those conventions even as AI techniques advanced. The author proposes some design patterns that would utilize advanced AI techniques, like AI as visualized where players can see how NPCs think and AI as role model where players mimic NPC behavior. In summary, the author argues that while today's AI could enable amazing new game designs, most games do not require advanced AI because they were designed when AI was much more limited. The author proposes game design patterns that could take advantage of modern AI techniques to inspire new AI-centered game design. The author discusses general intelligence in games to demonstrate. 1. Different AI systems have different levels of applicability and generality. While specific AI systems can solve particular problems effectively, more general AI systems that can perform a diverse range of tasks are often desirable. 2. The author organized AI competitions using car racing and Super Mario games to test different AI techniques. Competitors applied various AI techniques like fuzzy logic, reinforcement learning, and evolution algorithms. 3. The competitions revealed that more general AI techniques like a pathfinding could solve tasks in particularly effective ways. This shows the potential of more general AI techniques. 4. Games provide opportunities to test how general or specific different AI techniques are. By challenging AI systems with various game settings and tasks, we can gain insights into their strengths and limitations. In summary, the author discusses general intelligence in games to illustrate how game-based AI challenges and competitions can reveal the generality and applicability of different AI techniques. More general AI approaches tend to perform better across diverse game scenarios, though specific approaches can excel at particular tasks. Games thus provide a useful testbed for exploring the nature of general intelligence through studying AI systems. Here is a summary of the provided text. The author regrets that the book is almost over now. Though sad for readers, the author is happy to be done writing after the effort it took. The book started with the author's cats being rehomed and spread across 10 chapters exploring game design, AI in games, and intelligence in general. Competitions like GVG AI, which requires agents to play multiple new unseen games, are a small step toward general game playing and understanding intelligence. If an agent can learn to play the top 100 popular video games with human-like skill, that would indicate true artificial general intelligence. At the very least, it would greatly advance our understanding of intelligence. While progress has been made with agents that can play individual games well, there has been limited success with agents that can play multiple diverse games in a general way. Tailoring agents to specific games, rather than focusing on more general AI algorithms, seems to be a trend that may not bring us closer to general intelligence. Game-specific competitions risk becoming 2 steps forward, 1 step backward. In summary, the author discusses the potential of using games and game-playing AI competitions to help build generally intelligent agents. While noting some promising progress, the author also highlights limitations and risks, arguing that true general game-playing agents still lie in an unspecified future. Here are the key takeaways from the summarized notes. Games provide an ideal testbed for artificial intelligence research due to their ability to challenge diverse cognitive abilities in a structured and measurable way. Both board games and video games have been used as AI benchmarks, though video games offer a richer and more complex set of challenges. As AI techniques improve, they have the potential to transform games in significant ways, beyond just providing competent opponents. Content generation, player modeling, and adaptive game design are some possibilities enabled by machine learning and reasoning. Studying how humans and AI agents differ in their game playing and game design abilities can give us insights into the nature of intelligence and creativity. AI agents that can design compelling games would represent a major feat of computational creativity. The fields of AI for games and games for AI research feed into each other and benefit from mutual progress. There are many open research questions yet to be answered at the intersection of these two fields. The summarized notes recommend several books for further reading on topics related to AI in games. ranging from textbooks to design guides to more accessible introductions depending on your background and interests. Keeping up with the latest research requires following relevant conferences, journals, and researchers on social media. That's a high-level overview of the main ideas and recommended further resources based on the summarized notes. Let me know if you have any other questions. Here is a summary of the key points to have a successful career in computer science according to the book. 1. Develop strong problem-solving and analytical skills. Computer science is all about solving complex problems in an organized, step-by-step manner. 2. Gain proficiency in programming and software development. Mastery of programming languages like Python, Java, and C++ is fundamental for a career in computer science. 3. Gain a solid foundation in core CS subjects like data structures, algorithms, operating systems, and databases. These underlie most applications and systems developed today. 4. Develop teamwork, communication and presentation skills. Many computer science careers involve working in teams and interfacing with others. 5. Continue learning new technologies. The field is constantly evolving, so you must keep up with trends and new developments. 6. Build projects to develop experience and showcase your skills. Personal projects demonstrate initiative and practical skills to potential employers. 7. Pursue internships to gain real-world experience. Internships provide valuable experience, industry exposure, and networking opportunities. 8. Consider getting a graduate degree for more specialized roles. Areas like AI, machine learning, and cybersecurity often require an advanced degree. In summary, a successful CS career combines technical skills and knowledge with soft skills, experience, and a passion for learning and problem-solving through technology. Developing these areas through projects, internships, and continued learning will help you excel in computer science. Here is a summary of the key points from Riener et al., 2015. 1. The paper presents 10 patterns for procedural content generation, PCG, in games. The patterns provide design knowledge for game developers to incorporate PCG in their games. 2. The patterns cover a range of aspects, from level generation to rule generation to storytelling. Some example patterns are: content as objectives. The content is generated to match specific desired objectives or target attributes. Holistic twin. 2 generators are used, one that generates local content and one that generates global content, and they cooperate to create fully formed content. Mixing content. Existing content is combined or modified to generate new content. 3. Along with describing the patterns in detail, the paper also provides 2 game prototypes that illustrate and explore some of the patterns in practice. 4. The patterns are intended to serve as a starting point for utilizing PCG in game development, and the authors acknowledge that many more patterns likely exist. That covers the most important points regarding the patterns presented in Riener et al., 2015. Let me know if you need any clarification or have additional questions. Here is a summary of the key points regarding studies in machine learning using the game of checkers. Researchers from IBM created a checkers playing program that is capable of defeating the best human players. They used machine learning algorithms and a robust evaluation function to train the program. The researchers developed a new approach for learning combinatorial game strategies that combines domain-specific knowledge with machine learning techniques. This hybrid approach was crucial for achieving expert-level performance. The program, named Chinook, was trained on a database of over 1 million training games. It uses a combination of minimax search and alpha-beta pruning to evaluate board positions and possible moves. Chinook defeated the defending world champion checkers player in 2007, demonstrating that the game of checkers has been solved using AI techniques. The researchers discussed the challenges involved in developing expert machine learning systems for games, including feature selection, generalization, and scalability to massive training data and search spaces. The study shows how machine learning techniques can be applied to games to achieve expert-level performance and solve long-standing challenges in the domain of artificial intelligence. Does this accurately summarize the key points regarding the studies described? Let me know if you need any clarification or have additional questions. Here is a summary of the key points in the book. 1. The book discusses how artificial intelligence and games are related. It starts with a history of AI in games, how computers play chess using the minimax algorithm. 2. It questions whether intelligence is needed to play games and whether playing games involves learning. 3. The book then explores what intelligence is and what constitutes artificial intelligence. It discusses limitations of AI in current video games. 4. It covers how neural networks can be used to automate creativity and generate game content. The random number God algorithm is discussed as an approach to automated game design. 5. The book proposes design patterns for AI in games and discusses general video game AI and general video game playing. 6. In summary, the book argues that while current video game AI is still limited, games have the potential to serve as testbeds for developing artificial intelligence and advancing the field. Games can help push the boundaries of AI and enable more human-like intelligent behaviors. The key themes are the relationship between AI and games, the potential for games to drive progress in AI research, and the limitations of current game AI. The book covers a range of topics from foundational concepts to specific algorithms to design implications.